Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, it's my great pleasure to welcome Haiyin Shen to come to Microsoft and give a talk. Ms. Shen get her PhD degree from Weinstein University in year 2006. Currently, she is an assistant professor in Clemson University with focus on peer-to-peer systems, distributed computing, and various solutions. She has published more than 60 research papers in various top journals and conferences, has been a programming committee on many international conferences. Without further ado, let's hear what Professor Shen has to say about efficient and effective file replication and consistency management maintenance in peer-to-peer systems.
Thank you, Jim. Good afternoon, everyone. It's my great pleasure to give a presentation in Microsoft. I would like to thank Jim for the invitation. My name is Haiyin Shen. I'm assistant professor in the Clemson University in the EC department. The topic of my presentation is efficient and effective file replication and consistency maintenance in P2P systems. Now, first, I would like to briefly introduce my research areas. My research is mainly focused on distributed and parallel computer networks and computer systems, including P2P and content delivery networks, high-performance grid computing, mobile computing, and so on. I have been conducting research in peer-to-peer systems since I was a PhD student in 2002. In this area, I have been working on topology for scalable lookups, load balancing, congestion control, file replication, consistency maintenance, and so on. Recently, I'm working on the video streaming. In mobile computing, I have been working on the routing, reputation systems, energy efficiency, social network, and so on. This presentation is based on two publications in IEEE Transactions on Parallel and Computer Systems in 2009. Now let's see the outline. First is introduction, and then I will introduce the background and the related works about file replication and consistency maintenance. After that, I'll present our methods, including IRM, integrated file replication and consistency maintenance, and GeWave, geographically-aware wave for file consistency maintenance. And then I'll present our evaluation results, and finally I'll conclude my presentation. All right, as we know that in opposite to client and server architecture, peer-to-peer is a completely decentralized system. It's well known for its high scalability, reliability, dynamism, resilience, self-organizing, and so on. BitTorrent and overnight applications of P2P networks, which are widely used nowadays. This talk is focused on structured peer-to-peer systems, but the methods can also be applied to unstructured P2P. Now, in P2P file sharing system, every node has a routing table recording its neighbors. So when a node requests a file, the request will be forwarded to the file's destination, and then the file will be sent back to the requester. In P2P file sharing systems, the file access is highly repetitive and skewed towards the most popular ones. So if a node becomes a hotspot, there will be a delayed response. File replication is one solution to deal with such problems. It replicates a file to some other nodes in order to distribute the query load among a number of nodes and to avoid a hotspot so that the file query efficiency can be enhanced. File replication needs file consistency maintenance in order to keep the consistency between a file and its replicas. For example, if a file is changed, so all its replicas should be updated correspondingly. For example, in eBay transactions, in shared calendar, in banking, in flight control systems, we all need consistency maintenance to maintain the consistency between the replicas and the file. Now, Randy used eBay's architectural principle. He proposed eBay's five commandments. One of the 5 commandments is embrace inconsistency. 99% eBay stuff is based on inconsistency, and only 1% of transactions are based on consistency. So this time I come to Seattle to attend the P2P conference. So the presenter of the keynote this morning, who's Dr. Ken Berman from Cornell University, he mentioned that today's embrace of inconsistency has given us scalable service, but we just cannot trust. So he mentioned that consistency maintenance is really very important in our daily life or in the realm of business. Now, next let me introduce the related works of file replication. Previous work of file replication can be classified to 3 categories. The first method replicates a file in the nodes close to the file owner. The second method replicates a file in the requester. And then the third method replicates a file along the nodes in the path length. So we can see maybe the requester no longer requests the file later on. So the replica, but the replica is still there. Maybe the nodes along the path will not receive the request later on. So the drawback of previous method is that those methods cannot adapt to time-varying utilization replicas. They may be utilized now recently, they may be underutilized later on. So they cannot adaptively adjust to the time-varying utilization. Second, it's difficult to ensure that all replicas are fully utilized. For example, the replicas in requester actually is not shared by other nodes. Only when the requester requests the file later on, it can get the file from itself. And also those methods generate high overhead for unnecessary replicas and consistency maintenance, because the more replicas, the higher overhead for consistency maintenance, right? So let's see some representative works for file replication. So this work replicates a file to nodes close to the file owner. So the advantage of this method is that it can enhance the replica hit rate, because when the requests are forwarded to the server, the requests can always encounter the replica nodes around the server. And also it can enhance the lookup efficiency. But the disadvantage is that it produces overloaded nodes, because the replica node are nodes around the server. So there are only a few options. That's why those nodes may be overloaded. And also, it cannot significantly improve the query efficiency. Why? Because the requests encounter the replica nodes only when it is close to the server, right? So it cannot significantly improve reduce the path length. So that is one method. Another method replicates a file to requesters. So the advantage is that it can enhance the lookup efficiency, because when the requester requests the file again, and it can get the file from itself. But however, it has low replica hit rate, because this replica is not shared by others. It can only use it by itself. Another method is to replicate a file to nodes along the path length, along the path. So of course, it can enhance the replica hit rate because there are a lot more replicas along the path. And also it can significantly enhance lookup efficiency. So the drawback is it has significantly more replicas, so it generates high overhead. Now let's see the related work of consistency maintenance. The previous work for consistency maintenance can be classified to two groups. One is structure-based method. Another is message spreading methods. In structure-based methods, all nodes constitute a structure, such as hierarchical structure, tree structure, but we know that P2P is characterized by churn. Nodes leave and join continuously and frequently. So for the structure-based method, the dynamism leads to unsuccessful update propagation. That means in a tree, if a node fails and all of its children cannot get the update successfully. Okay? And also dynamism leads to high structure maintenance overhead. Okay, that is structure. There's extra overhead for maintenance. Message spreading methods such as broadcasting, gossip, random walk. So of course they lead to tremendously redundant messages. And also one node may receive more than one update. And also they cannot guarantee every replica node can get the update. So those are the drawbacks of the two kind of methods. So basically, the drawbacks of previous work is that they cannot guarantee successful update and they generate high overhead. So the essential problem is passively accepting update messages makes it difficult to avoid unnecessary update. Why? Because replica nodes are just waiting for the update. They cannot control whether they should ask for update or when they ask for the update. So that's why they have those drawbacks. And also we observed that for some files, the query frequency is less than update frequency. A file may be updated very frequently, but it's requested in a less frequency, so that every time the file is updated, there is an update, but it's requested less frequency. So in previous work, they try to guarantee that every time a file is changed, there is an update. But we lose the strict requirement. We want to guarantee that when a requester receives the file, it is updated file. It doesn't matter how many updates are executed. All right, now let's see some representative work. This work is published in 2008, IEEE Transactions of Parallel Distributed Systems. So they build a hierarchical structure. Those nodes are high-capacity nodes, and physically closed nodes constitute a tree. So the replica update is forwarded along the high-capacity nodes and then further forwarded along the tree. And this is another structure-based work proposed in 2005. Basically, they build a tree based on all the nodes in the system. And every node has an index indicating whether its children have the replica or not. If its children doesn't have the replicas, the propagation stops here. Otherwise, the propagation will be further forwarded to its children. Now, this work is message spreading method, push and pull. So normally, nodes use rumor spreading for update. And only when a new node joins in the system, it will pull the replica nodes to pull update. So we found that there's interdependency between file replication and consistency maintenance. The file replication needs to minimize the number of replicas in order to minimize the overhead of consistency maintenance. On the other hand, consistency maintenance needs to help file replication to keep the consistency between a file and its replicas in dynamism. So integrating these two techniques can enhance their mutual interactions, can avoid their conflicting behaviors, and can ensure that the two techniques can be exploited to their fullest capacity. Therefore, we propose IRM integrated file replication and consistency maintenance in a harmonic and coordinated manner. Unfortunately, previous work addresses these two issues separately. So that's why we propose a method that combines them in a coordinated manner. The features of IRM include high effectiveness and low cost. So basically, each node in the system actively decide whether to create or delete a replica and actively pause for the update rather than passively waiting for the update. A node replicates highly queried files and pause at a high frequency for frequently updated and queried files. So IRM avoids unnecessary file replications and updates by dynamically adapting to time-varying file query and update rates so that it improves replica hit rate, improves replica utilization, improves file query efficiency, and the consistency fidelity. All right, now let's see the issues addressed in IRM. File replication. Where to replicate files so that the file query can be significantly expedited and the replicas can be fully utilized. We don't want to see underutilized replica because it's a waste of overhead. And how to remove underutilized file replicas so that the overhead of consistency maintenance is minimized. Now, in consistency maintenance, there are also two issues. One is how to determine the frequency that a replica node probes a file owner in order to guarantee timely file update. If it probes too fast, it's a waste of resource. But if it probes too slow, maybe the file will not be updated in a timely manner. Okay. The next issue is how to reduce the number of polling operations to save cost and meanwhile provide the fidelity of consistency maintenance. Overview of IRM. So in peer-to-peer file sharing systems, some nodes have much higher traffic load than other nodes due to three reasons. First is node interests are different. So there are a lot more traffic between the interested nodes and the file owner than the node who's not interested in the file. Second, file popularity is non-uniform and time varying. So a file may be popular at this time, but it may not be popular at that time. Third, nodes are located in different places and may have different number of neighbors in P2P overlay network. Now let's see an overview of IRM. For file replication, we can see that traffic junction nodes carry more traffic load. So IRM replicates files in frequent requesters and traffic junction nodes in order to improve the utilization of replica. Now this is IRM for file replication. For consistency maintenance, the replica nodes will actively poll the file owner for the update. Now let's see the details. In the case when a file requester requests a file, we define query initiating rate for file F as the number of queries for F sent by the requester during a unit time, denoted by QF. So we set a threshold for that query initiating rate, TQ. So when a file requester's QF is greater than TQ, it replicates the file. Now for the case that a traffic junction node replicates a file, we define query passing rate of a file F as the number of queries for F received and forwarded by the node during a unit time, denoted by LF. So we set a threshold TL. When LF is greater than TL, the node add a replica request to the file requester, and then the file owner will send the file to the replica requesters. Now let's see the process. So those nodes will check whether their LF is greater than TL. If yes, they include a file replica requester into the file requester. And then after the server receives the request, the server will replicate the file to the replica requesters, and also send the file back to the requester. And then the requester checks its QF. If QF is greater than TQ, the requester will replicate the file. Now, another problem is the server may receive a lot of requesters, but how the server can determine whether it should replicate the file to the requester or not. So we define the server as the original file owner and the replica nodes. So a server's query load is L. It's defined as the visit rate during T. And server's capacity C is represented by the number of queries it can respond during T. Now, there is a factor gamma. The server I periodically checks its LI. If its load over capacity is greater than the alpha, it releases actual load. If it is less than 1 over alpha, it will determine whether it replicates the file or not. If the benefit is greater than cost, then it will replicate the replicated file. Otherwise, it does nothing. All right. Now, the file replicas may become underutilized. So in this case, the replica nodes periodically check their load. If the load is less than TL, they remove the file replica, so that IRM ensures that all replicas are fully utilized. There's no waste of overhead for maintaining the replicas or for the consistency maintenance. Okay, next is how to appropriately determine the value of QF and LF. For example, maybe the requester is very interested in a file at this time, but next time period it lost the interest. And then later on, it's interested in the file again, so that there will be a fluctuation of replica creation, replica removal, replica creation. So in order to avoid the resource waste for the fluctuation, the IRM employs exponential moving average technique to reasonably determine file query rate over time t. So basically, it has a factor. So it does not discard the old observation, but it still uses the new observation. So this is the formula for determining the query rate. Okay. Now, recall that in IRM, replica nodes post the file owner for update. Okay, let's see the benefits of polling. It can reduce redundant updates. So a node does not necessarily need to update its replica after each update. As I mentioned, a file may be updated frequently, but the request is coming less frequently. So we just want to make sure the requester receives the updated file. So every time when a file is updated, the node does not have to update it until there's a request.
Question. When the request actually comes in, do we need to check and verify if the file is of the latest version still?
Yes.
Okay. So at the time the request actually comes in, we still need to do a verification with the original server, right?
No, it does not do the verification on purpose. For example, when I receive the request, I'm still in the process of polling, then I just wait. I hold the request until I get the updated file. But if I'm sure this is the updated file so far, then I just respond.
So even if this may not be the true
up-to-date file. Yes,
version, right?
yes,
okay.
yes.
So in that case, you can still have some inconsistency.
Right, right. Yes, relatively. I will introduce the details later. Okay, next is it can enhance the fidelity of consistency guarantee of query results. So that's what Jim mentioned. When a node is in the process of polling, there comes a request, the node will hold the request. And then after it gets the up-to-date file, it will respond to the request. Third, it enhances consistency guarantee in churn. Instead of passively waiting for updates which may lead to update failures due to node failures or departures, a node can actively poll to get timely update. For example, in a structure, if a node left, then its children cannot get the update successfully. So in polling, so a node just polls the file owner for update. So there's no unsuccessful update. Yes?
It assumes that there is an owner for every file, and this owner is always up.
Right.
So how do you deal with, so there is no system when you can just put a file into the P2P system. Usually use replicas to guarantee availability. In your case, practically means that if owner is down, the whole system is down practically, right?
Right. Yes, that is a question when I was coming here. I was thinking when I was on the way. So actually, if there's no replica, if the service is down, the file is not available anymore, right?
If there is replica. Oh,
if there's no replica.
Okay.
So yes, that is really very good question. So in our work, we just assume the replica helps the server to serve the clients. But if the server is down, all replicas are invalid. All replicas, we assume they are down. They are not available. The original file is gone. But this is the problem actually goes back to the node failure in P2P, right? In P2P can handle node joins, node departures, but P2P cannot handle node failures. If a node fails, then all files are lost, right? Okay. So yes, so this problem actually, I think it should be addressed by the P2P itself, the traditional research work, rather than the replication and consistency maintenance. Good point. Okay, let's go on. It helps to guarantee timely update for all replicas because in traditional update propagation, the update may be forwarded by a number of relay nodes before it arrives at the replica node. But in polling, the transmission is directly between the file server and the replica node. So there's no delay. Yes?
So what's the reason to have relay nodes in general in P2P? So my understanding was that you use relay nodes because you usually cannot reach directly other nodes, and you create the tree.
Right.
So there is in some situations you just won't have direct route from the node to the master node, right?
The reason is to conduct the consistency in a distributed manner. For example, here, this is structure. So the node, the replica update is forwarded or propagated among the parents first, and then they will be further forwarded along the tree. All this structure. So the reason to build a structure for propagation is in order to do the propagation in a decentralized way.
But it kind of assumes that, but it doesn't guarantee that there is direct route, a direct way to connect to any node, right?
It's easy.
Because in your case, you practically say, no, any node can talk to any node, right? And in P2P, you usually don't do that. Because when you check for updates directly, right?
Right,
you don't check through the intermediate nodes.
No.
I see here, there's basically different philosophies. So, I mean, on the internet, potentially any two nodes can try to establish a connection, right? I mean, not actually any two nodes can actually establish a connection because there's net traversal firewalls basically holding things in between. And the establish a connection actually is expensive operation. Even if two nodes, I mean, can basically connect through net traversal operations, it takes time. Because, I mean, basically all the traversal operations you need to go through. And there, I would say there's two basic aspects. One is topology building, which I don't see covered here. So it's basically like this. Say, I mean, let's say, I mean, we have a huge popular social network like Facebook or something, and we all participate. From time to time, I want content. So one part, basically, potential operation is that each time I want a new content, we form a new cluster. So when I basically, let's say, look at this set of photos, my node is going to join a new cluster, open and establish connection among themselves and try to pull their content. The work discussed here, more assuming you have a more stable network. So it's like, for example, when you boot your machine, the machine just joined a big cloud, maybe a PNRP cloud, a DHT cloud, a core cloud or something. Then, I mean, you basically request content through overlay routing in this cloud. This way, you do not have the establishment cost on basically peer connection, but you do incur routing cost because your content is going to route along the way. And I would argue that a better solution probably is a combination of two. Sometimes you need to evolve the topology. Sometimes you probably need to do routing as well.
Yeah, no, my only question is, you practically kill the topology and routing because you practically say that to poll for updates, you need to connect to node directly. Do I understand it correctly?
Right.
So practically everyone who asked for that file will actually go to the owner.
Right.
Do direct connection to the owner.
Yes. Again, good point. This is the work so far, and then I will introduce a structure that can conduct the consistency maintenance in a decentral, distributed way. It is a good point. Okay. Because if all nodes pull the server will become a hotspot. It will be overloaded. And also I agree with you. It is against the P2P principle, this distribution, right? Decentralized manner. All right, let's go on. The TTR is time to refresh. So the nodes will poll for update every TTR. So the question is how to determine TTR so that the polling is conducted at approximately the same rate as file update rate. We don't want to specify a fixed rate because if it's too faster, it's a resource waste. If it's too slow, it cannot guarantee the files are up to date. So how to determine? This is very interesting. So the IRM relies on linear increase multiplicative decrease algorithms. Now, a file's maximum update rate is 1 over delta t, and the TTR is set to delta t initially. So when replica nodes polls the file owner, if the file does not change between successive polls, the TTR equals to TTR old plus alpha. Otherwise, It's equals to TTR old divided by beta. Now, in order to limit the TTR within certain range, we specify TTR mean and TTR maximum and use this formula to limit the TTR to a certain range, so that the polling is conducted at approximately the same rate as file update. As a result, this consistency maintenance algorithm can avoid unsuccessful update in dynamism with less overhead. Okay. So another observation is that query frequency, when query frequency is less than polling frequency, it's an overhead waste to poll the file's owners. I mentioned this issue several times. Now let's see example. Why? If this file replica node polls twice per second, once, twice per second, but this replica is requested only once per second, so it does not have to update twice per second. It only needs to update once per second, because our goal is to ensure the file is up to date when it's requested. Our goal is not to guarantee the file is always up to date. Okay, so that we define if the TTR is no more than file query frequency, it will be equal to file query frequency. Do I make myself clear here? This is a very important observation because no previous work deals with this problem, so that the polling overhead can be reduced.
Because usually files change periodically, and with given frequency, do you really observe it in real world?
No, unfortunately no, but we really do want to, to have the observation in real world, in real application. Okay, so now let's go back to your question. Yes, so if all nodes pose the file server, the server will be overloaded, and also it's against the principle P2P. All right, so we develop the GeWave file consistency maintenance. Two goals. One is it enables propagation be conducted among geographically close nodes, or in P2P area we call topology aware, locality aware, or proximity aware, right? And the second is decentralized way. Now, before I introduce GeWave, let me introduce the helper number. We have a number of landmark nodes. We measured the distances between each node and the landmark nodes. And each node will have a landmark vector. So physically closed nodes have similar landmark vectors. And then we use Hilbert curve to transform d-dimensional vector to one-dimension ID. And we can see that if you, here in d-dimensional space, u is close to u prime but farther away from v, after the d-dimensional space is transformed to one-dimension space, u is still close to u prime but is farther away from v. So that's the feature of Hilbert curve. It can preserve the closeness of nodes in the dimension reduction, so that the similar landmark vectors will be transformed to close Hilbert number. And then we know that physically closed nodes have similar landmark vectors, so they will have similar Hilbert numbers. If they have the same Hilbert numbers, they are physically close. If they have totally different Hilbert numbers, they are physically far away from each other. Okay, so this is the GeWave. The GeWave is built dynamically based on node geographical location and the polling rate. So we can see that it takes the file owner as the tree root and constitutes nodes into different layers based on polling rate levels. Nodes in the up layers having high polling frequency than those in the lower layers, so that it ensures that the parents always have up-to-date file earlier than the children. The children can poll their parents for the update. And also, those nodes are physically closed nodes. DEF, DEFG, okay? So they have the same Hilbert number, 5. So the GeWave connects the geographically closed nodes together. And an update is propagated in the fashion of top-down wave between geographically nodes. Okay, so it's updated in this way because those nodes have higher frequency than the lower level nodes. Therefore, the children can poll their parents for the update. And also we can find that the polling is between the physically closed nodes. So the overhead is reduced because the transmission is in close distance. So therefore, the GeWave achieves the two goals. One is the propagation or polling is conducted in a decentralized manner, and also the polling is conducted between physically closed nodes. Any questions? Okay, basically here, the children, the nodes in level 4 polls the nodes in level 3, and actually it's from the top to the bottom. Nodes in level 1 polls file owner. Nodes in level 2 polls nodes in level 1. Nodes in level 3 poll nodes in level 2. Okay, and physically closed nodes, they poll each other. Now let's see the GeWave structure maintenance. So actually, the file owner is controlling the nodes. So it will collect the information, including TTR and H of its replica nodes, and then it locates the replica node in the tree. And for replica node departure, the node will notify its neighbors, predecessor and successor, that it's leaving. And the leaving node transfers its children to its neighbors. For example, if 2 leaves this tree, it will transfer its children to its neighbor 2 here. Okay. And then replica node failure. So for failure, it's easy. If this node polls its parent, but it does not get a response during certain time, and then it just go back to the original method. It polls the file owner. Okay, and that's why it is dynamism resilient. Replica node mobility. So the node TTR may be changed. So when the TTR is increased, it will traverse along the tree until it reaches its level, and then traverse in horizontal direction, because all those values are ordered in ascending order. Okay, so that is replica node mobility.
This structure deals with the change in the polling pattern of a file. Let's say, I'm currently interested in this particular images. After a while, I'm not interested in this anymore. So I'm stop requesting that content. How is this structure going to be involved?
All those nodes are replica nodes.
Okay. And how but the replicas nodes, their requesting rate is determined by the user request.
Right.
What I'm asking is that if the user's request frequency changes, let's say maybe in this period of time, this set of users more active. Later, they're not interested in that file. That changes. Is this structure going to reorder, or it's going to stay?
If users' interest, yes. So when replica is underutilized, if users are not interested in the file any longer, so the replica will be removed, right? Okay. In order to guarantee every replica has a high utilization. Yep. So that is replica node departure.
Okay. So in that case, the replica node will depart from that basic systems.
Yes.
If a node have increase in terms of my utilization. Maybe, I mean, in the past I only
Right.
pulling very infrequently.
Yeah.
When I
Then there
started
will
pulling
be
quite
more replica nodes, and then this is replica node creation.
Okay. But let's say I already have a replica node created, but in the past that frequency is low. Later the frequency of that node increases. How is that going to? Is that node going to move up?
If the frequency increases, we have threshold. So if the frequency is higher than the threshold, there is only one replica. But definitely, nearby nodes will have higher request frequency. So nearby nodes will also have replicas.
I notice in this scheme, because I mean, one distinctive feature is that you're starting to change topology, right? I
You
mean,
build another topology.
you're starting to build another topology based on basic usage patterns. When will you start to build a topology? When will you just use existing topology completely?
When start to build the topology, when start to pull. So when there's node, even if there's one node, then this topology can be built. It's like P2P. So initially there's only one node, and then when the second node joins in the system, they're connected. When the third node joins the system and they are connected, finally they becomes maybe.
So what's the use case? I really don't understand that, because for me these systems usually have large number of files.
Right.
And these files are usually, there is not very good periodicity of requesting those files. And it looks like you will practically, if I have a million files on my hard drive, or like 100K files which I am sharing, and I have people requesting them, it will mean that I will have 100K topologies. And some of these, my node can potentially connect to 100K servers just because the topology is very different. And also, I just don't, what's the use case to requesting the same file periodically? It looks like more like messaging system with limited number of topics.
Okay.
Pool-based messaging system rather than file storage or something like that.
Okay. So it's true in Kazaa or Morpheus, the file hardly change. But currently there are more and more applications that need consistency maintenance. For example, shared calendar, right? Shared calendar. I change my calendar, some others change calendar, we need to see each other.
So you practically built a messaging system, queuing system.
Yes, message that is, or
Like
banking.
call-based queuing system, but it's not file sharing system, it's more like I mean, maybe it's the right thing, I just mean that use case is not file sharing really.
The user case can be applied to the applications that have frequently updated contents.
A limited number of those files.
Limited, yes. Or banking, stock market.
So, small number of frequently changed files. So it's like messaging.
I think in real cases, what you have is a large number of files, only a small number of them changes.
So then it doesn't apply to that. So my point is that it applies to different use case than file sharing. It's more like messaging system, and you have frequent updates of small number of data content, right?
It can also apply to the file sharing. Why it cannot?
You need to deal with those code files. You need to deal with those files.
So
which
I'll give an example. You have 100K files, right? And for example, you have, I don't know, 100K nodes, like, I don't know, 1,000 nodes, each of them have 10K files. They're sharing these files, like you do in P2P. This will create practically a mess, because you will practically have very dynamic structure and per file.
Right.
So your topology is per file, not per, and I don't understand how it would really function in real life.
It's true, but as the keynote this morning, the keynote presenter mentioned, there's a conflict between scalability and consistency maintenance. In order to achieve higher scalability, we need to resort to such a structure. We cannot use broadcasting, message spreading, or gossip. But on the other hand, you're right. To maintain such a structure for each file, it may lead to high overhead, but there is a trade-off.
I think, consistency can be solved in different ways. The way I see consistency solved is that you do not guarantee the consistency, or you guarantee the latest versions.
Right.
But you basically make sure, basically later you can have a way to resolve conflict. So I mean, for example, live mesh is basically such a system. You basically each file you attach with it a version vector that basically is the change history of these files. Now, I mean, the server can go down. And you can leave replicas, which is old replicas around. That means when I retrieve a file, I may retrieve an older version of the file, but that's fine. The problem is that when later that server comes up again, and if we meet, the system will figure out which one is later and deliver the newer version to me. And that way you can solve consistency to some degree. You can still have consistency, basically branches. Meaning, for example, the server, I mean, can go off, and we each make our modifications. Let's say
but here consistency is already solved. It actually says if file owner is down, we don't serve the file.
Yeah.
So
this is one way. It's a way to solve consistency. Let's say it's expensive.
Okay.
And then I would say it's not a good experience, right? And that means when the server is down, that file becomes unavailable.
Okay.
I mean, usually I will argue you want more availability. I want to tolerate consistency.
Yes. But
I mean, imagine basically you and I co-edit a document. You want the document to be editable. Not to say, okay, when you are the owner, you are gone, well, I will not be able to edit the document.
then we go into the whole dynamism talk.
OneNote does that. OneNote allows for disconnected update of a shared document because it basically, if you look at the document structure on disk, it's a change history with branches, and they have an automated mechanism.
It's basically a mechanism to merge the branch.
It's source code control.
So, yeah, actually the application depends. Some systems, some application needs very strict consistency maintenance. Like the presenter this morning, he gave us an example, like airplane control system. You know, if they are not consistency, this system say, okay, there's no plane, go up, and that system says there's no plane, go down.
I mean, I think nowadays there's more and more application that don't demonstrate consistency. It is true, you have systems demand strict consistency. Banking system, airline reservation system, is that examples. But those examples serve basically pretty well with server-client structure. So you basically all stored structure in one place. Every time you want the basic status, go to that particular server.
Yes, yes. But
that server okay.
Right.
I mean, the majority of the case when we're dealing with internal scalability, you need to have some consistency. When you think about Facebook, basically MySpace, Microsoft Space, I mean, gazillions application where you have huge amount of data. Do you care to, I mean, have absolute consistency? Probably not. You can survive without consistency.
Yeah, the client-server model sometimes works much better than maybe decentralized.
If you demand absolute
yes,
consistency.
like a Google search. But then we should discuss the problem. Is P2P really, does P2P really have more advantage than the client-server model? So for P2P researchers, we always say, okay, P2P decentralized, it has high scalability. It's better than client-server. But is it really true?
I'm not arguing peer-to-peer is basically good for every application, for every scenario. It's good in scenarios where you demand scalability. I mean, if your demand is absolute consistency, airline resolutions, don't bother building a peer-to-peer system.
We will see.
That's the way I argue.
Okay. Yeah, we can discuss it offline because I always in favor of P2P. I think when there are a lot of users, a lot of nodes, it's better to use P2P.
I would say peer-to-peer is not for every application. It's not that case.
Okay. All right. So let's go on. I'll present the performance evaluation. So we compared IRM with the three category of works: server-side, client-side, and pass. So server recall that server-side replicates file on the other server, client-side on the other client, and pass along the nodes in the pass. So let's see the performance. Here, this metric is replica hit rate. We hope that the replication method can have higher hit rate. So there's less underutilized replicas. So from the figure, we can see that pass has higher hit rate than IRM, and then IRM has higher hit rate than server side and client side. It's understandable that these three methods have the same number of replicas because every time a server is overloaded, it creates a replica. So they have the same number of replicas, but pass replicates file in all nodes along the routing path. So it's understandable because it has much more replicas. That's why it has much higher replica hit rate. Now this is node utilization. I didn't introduce the load balancing idea in my presentation. So basically, when IRM generates replicas, it considers node available capacity, but other methods do not. That's why IRM can always restrict the node utilization around the one, but others, maybe like this client server, it has high node utilization. Some nodes may be overloaded. So overhead of file replication. The y-axis is number of file replicas. It's very easy to understand this figure because path replicates all the in all the nodes in a routing path. That's why it has a lot of replicas. But not, yeah.
Actively pushes updates?
Could you please say it again?
Is it the one which actively pushes updates?
No. Here we just compare the file replication method. Those three methods are all file replication methods. That's why I said previous work addressed file replication and consistency separately. So we hope, we combine them in a coordinated manner. So why IRM generates less number of file replicas is because it removes the underutilized replicas. Okay, so it has a small number of file replicas. Now we also compared IRM with and without adaptation. So from the left figure, we can see that the IRM with and without adaptation almost have the same average routing path length and the replica hit rate. But the IRM without adaptation has more replicas than with adaptation. That means adaptation is good. It helps IRM to reduce the number of replicas. All right, and also we measured the average path length in churn. And we can see that IRM has slightly a little bit longer path length than pass. We all know the reason, right? It has much more replicas. And the server side and client side lead to significantly longer path lengths. The reason client side has longer path lengths is because if the requester is down, then the requester has to be forwarded in the original routing algorithm. Now let's see the maintenance. So we compared the GeWave with scope, UMPT, and push and pull. Those are the experiment settings. This figure shows the proximity-aware performance. The x-axis means the physical distance by hops, and the y-axis means the CDF or percent of messages. So from this figure, we can see the GeWave and the UMPT can always transmit almost 100% of messages within 10 hops. So the messages are transmitted within 10 hops. But in push and pull and scope, only 30% of messages are transmitted within 10 hops. So this means in these two methods, the messages are transmitted between physically close nodes. But these two methods, they don't consider the proximity. That's why these two methods have a high efficiency. Overhead, sorry, the letters may not be clear. Average number of messages. So this is the what x-axis means the number of replica nodes. So from this figure, we can see the GeWave leads to much less overhead than others. This message, number of messages, also included the messages for structure maintenance. And GeWave does not need maintenance. And these two methods need maintenance. And also push and pull, we understand. Message spreading, right? Must generate a lot more messages than others. So from this figure, we can conclude that GeWave generates much lower cost than other methods. Communication cost in churn. We define the communication cost as the product of the message size and the physical path length. And again, GeWave generates much less communication cost than others. There are two reasons. First, it has the messages propagated between physically closed nodes. Second, it has less messages than others. Effectiveness of consistency maintenance. So we hope that with consistency maintenance mechanism, a request always can get the up-to-date file. So this y-axis means the number of up-to-date files received. Now from this figure, we can see GeWave and push and pull can always get the updated files, but push the scope and the UMPT cannot guarantee that the requesters received up-to-date files. Why? Because they are based on structure. So in structure, if a node fails or node departs, before the structure is fixed, their children cannot get the update successfully. Okay, and the push and pull broadcasting, it is more dynamism resilient. All right, conclusions. So file replication and consistency maintenance are intimately connected, and the previous work just addressed these two issues separately. So we propose integrated file replication and consistency maintenance. Basically, nodes actively determine if they need to replicate a file or not, and they actively pause for the update. And also we propose GeWave to conduct the consistency maintenance in a decentralized manner. So briefly, they have two main features. One is high effectiveness, second is high efficiency. Okay, efficiency means low cost. Effectiveness means they will guarantee the file consistency. They will guarantee the file query efficiency can be improved. Thank you. Any questions and comments? Yes.
So you're practically saying that polling model is more efficient than push model, right?
Yes.
But
that's
that
my
assumes that you have a very small number of files. In your example, you have only 50 files. But if you have a scenario, you have like a couple million files or whatever pieces of information, and you need to poll for every piece if it's changed or not. Even if you don't change any of those, you will have pretty high traffic, right?
Push every time when a file is updated.
But let's say it doesn't update.
Huh?
If files don't...
Right.
For example, you have million files, but you update 1 file per second.
Okay.
You will have 1 message per second. If you have 2 million files and you don't update any, you will still have million messages per, I don't know how many your update frequency is.
Good question. And personally, actually, I believe, push and pull, they have their own advantages and disadvantages. They're suitable in different kind of situations. But in this method, let me see. Okay, here. It's not the file always pull the update. Using this algorithm, the file will be the file owner will be pulled at approximately the same rate as file update rate. So if the file
You usually don't know the update rate.
this is the feature of that algorithm, but it's not 100% accurate, I believe, but approximately. That's why I put approximately. So in the example you described, if there's no update, there's no polling.
But if you ask for the file, you still will need to do polling or not?
If I ask...
Not update rate, but like client request rate. For example, I want to show new content file every second. So you, as a client, right? Will you poll the owner every second or not?
Could you please
So no, but
describe
there is client, right? He
Uh-huh.
wants to see the file.
Mm-hmm.
So you said there is a rate which client requests the file.
Yes.
So is it related to update rate, or is it how you call it?
When
request
a
rate?
client wants a file, it just sends a request, right? And then
Right.
the request will be routed based on P2P routing algorithm. Why is related to consistency maintenance?
Yeah, because how do you know if he's getting the latest version? So client got a copy, right? Client requested the file.
Right,
It got downloaded. I have it in local cache.
right,
So next time ask for it in a second.
yes.
What happens in your case? Do you go and check with the owner if it's current copy, or you just return the copy?
Okay, I see, I got it. So the client have a cache. I think this is not related to this work. If there's a replication algorithm, say the client replicated it on purpose, and then later on when the client wants the file, it can get the previously achieved file, right? But if it's a normal case, without file replication, just to say file, a request to get file, usually it's stored in the cache, right? So that is operating system problem. So whether it will get a file from the cache or not.
Cache is, I mean, by cache, I mean this.
Okay. Okay. Then it needs to pull, right? It needs to pull the file owner for the update.
So if you have a large number of clients all reading, they will constantly pull.
Right. The
In
file.
a push model, they will get always local copy and only pull the server when they get notification that the update happened, right?
I think the point is that you really don't know the file update rate. It's really, it's not a deterministic process. I mean, sometimes the owner update the file frequently. Sometimes you will just leave it there. Think about basically when you work on a file, let's say you write a paper. Sometimes you basically do revisions quite frequently. Maybe then goes to sleep, the file leave it there, you don't update it at all. And then you started to update it again. So this process in the pool model, the pooling, the update rate is actually not known until you basically somehow the server somehow tell the client how frequent it's updated.
Also, if the update rate is very low, then the chances of getting an null copy is higher, right? Because the polling is not.
I think we can move the discussion, to basically a more, we can move to a conference room rather than use this room for basically more friendly discussions. Let's thank Professor Shen for the interesting talk.
Thank you very much.